Okay, so today we're going to be talking about invariance. The basic idea behind invariance is just you're looking at a combinatorial problem and you want to find something that does not change or always changes, and that's called a monovariant. So why don't I just hold on. So invariant is something that never changes. Uh, and usually this is in some kind of process. Uh, and monovariant changes in a very specific way. So oftentimes, what you want to do is you either want to find some type of pattern, like something that does not change, or something that always changes in a very specific way. Um, and this is a really common idea. It's just kind of like pigeonhole. It's the idea itself is not that hard to learn, right? But it's kind of hard to apply this idea to problems that you may find. So why don't we start with a simple example just to get started. Um, so if the numbers 1 through 2005 on board, on some blackboard, um, and we if we have a and b on the board, then we go to the absolute value of a minus b. And you keep on going until there's only one number left. Can final number be 2? So here, the idea is just to look at parity. So you just consider which numbers are even or which numbers are odd. And if you notice, um, if a and b are the same parity, then if a and b uh, same parity, then a minus b is even and else is odd, right? So if one of a and b is odd and the other is even, then we get like one odd, because we're only caring about parity here, so we're only going to care about odd numbers. So one odd goes to one odd, right? So if we have one odd, one even number, we go to one odd number. If we have two odds, then we go to zero odds, right? So the number of odds, always has the same parity as well. That means the sum of the numbers always has the same parity. So number of odd numbers, always odd as well. And that means that the last number has to be odd, right? Because if you only have one number and you have an odd number of odd numbers, then the last number is odd. Right. So this is just a simple example, just to get you familiar with like what kind of things can show up when you're looking at invariance. And so like looking at parity is one common theme in a lot of problems. And it's really important, like when you look at some problems that have some type of invariance as their solutions, it's not always obvious immediately what type of invariant will work. It's more about you just have to kind of look at what's going on and just kind of make a guess on what's going on, like what's happening, right? And then you want to like somehow prove it. So here's another example. So if you have a pile of 1,000 stones, 1,001 stones in pile. Choose some stones. Choose. Okay, so here's the process. So each step, take pile, remove a stone from, remove a stone, split pile into two non-empty piles. Okay, so why don't we look at some examples? So if we start from a pile of 1001, then we can go to something like 499 and 501, right? And we can keep on doing this. We can go to something like 499 and 1, and let's say it would be 499 again. And it's really not clear at this point what type of invariant you would want. So like, oh yeah, the question is, I forgot to write, the question is, can we have piles all threes? So it doesn't specify the number of piles that are all threes, but we just want to know, can we have eventually all the piles have size 3? So I guess a better example here would be, instead of making this 1, we should make this 3. So in this case, you would have 3 and you would have 497. And so the question is, can we have make a bunch of 3s? So what if we just tried the dumb method of just like making, every time we split, we always split into something like 3 and something else, right? So if we have like a pile of size x, then we go to 3 and x minus 4, right? So every time we create a pile of size 3, this value has to go down by exactly 4, right? And so that means that if we want to split, so our conjecture would be something like if every time we create a pile of size 3, x goes down by 4, then we might want to assume that x has to be 3 mod 4, right? Because eventually we want something like 7 goes to 3 and 3, right? And because we need all the piles to be 3, so we can't have something like 6 goes to 2 and 3, because then 2 cannot somehow go to 3. If x can be split, f can be split all 3s, then x is 3 mod 4. And, okay. And so, so basically, but how can we prove this, right? Like, so far, we've just been experimenting and we've come up with this conjecture. So how do we actually prove this? Well, we want to find some type of invariant, right? I guess that's the idea of the class. But like, if you were not taking this class and you just like saw this problem randomly, how would you know to use invariant? Well, the idea is, if you come up with a conjecture and the conjecture involves some type of invariant, and the invariant here is x should be 3 mod 4, right? That's like something that does not change. Then we want to somehow prove this using some other invariant. And I'll show you what I mean. So what you notice is that if you have something like x, you go to x, or you go to a, then and x minus a minus 1, then or like this characterizes all possible moves, right? You remove one stone from the pile of x, and then you split the remaining x minus 1 things into a pile of a and a pile of x minus a minus 1. And this basically covers all the possible moves we can have. So the idea is, what stays invariant here, right? Well, what stays invariant here is number of stones plus number of piles, right? Because every time, every time we split a pile, we take away one stone, but we add a pile. We go from 1 pile to 2 piles, right? Is invariant. So how can we use this? Well, we want to somehow go back to our mod 4 idea. So if you have a pile, let's say we have a bunch of 3s, right? So now we're looking at the end state. We're going to go for like a proof with contradiction. So we're looking at the end state and somehow showing that it's not possible. Then if there are k piles, then number of stones plus number of piles equals 4k, right? Because we have 3k stones and k piles. But the thing is, 4 does not divide 1001, so we have contradiction. and we have proven it. So if you notice from the strategy that we tried to solve the last problem, oh yeah, so I'll go over some strategies now that we've seen some examples. Try to look at the most basic, zoom in on the most basic structures. For example, what the most basic structure for the last problem would be x, or I'll say, for example, i.e. X goes to a and x minus a minus 1, right? This is the most basic structure for our last problem with the blackboard, or with the stones, because like this characterizes everything, right? This characterizes every single move um, out there. Um, and if we can find some invariant in this, then we can generalize this invariant to everywhere else, right? And here we just notice that if we every time we make a move, the number of stones decreases by 1 and the number of piles increases by 1. And so here we're just zooming in on some basic structures, and I guess I'll number these as well. Let me number this as 1. Let me go to 2. So strategy 2 would be finding patterns, plus make conjectures. Making conjectures is probably the hardest part in combinatorics, or really all Olympiads in general. Hardest part. And it's, I mean, I wish I could go more into like how to make conjectures, but honestly, there's not really too much. It's something that you have to find out by yourself, right? Once you get more experience with how to solve problems, you should be able to more easily come up with ways on how to make conjectures, and this is one of the main skills you have to learn by doing more Olympiad problems. Um, and finally, the third strategy for invariance would be third strategy is just experimenting with the process, because like you're given a process in most invariant problems or monovariant problems, you're given some type of process, right? It's not just still. You're either, like, the problem describes like splitting up piles of stones or like rewriting numbers. So just like blindly experiment. I think a lot of people underestimate this. So don't underestimate this. If you're stuck, just experiment. Um, because you'll gain a lot more understanding about what's going on with the experimenting. When I'm presenting this to you, problems to you in this class, like, I'm probably not going to do as much experimenting as you should, because obviously I know the solution already, so, and I don't want to like waste too much class time, so I won't be doing that much. But you should, when you're solving problems, don't be afraid to spend the majority of your time just experimenting, and not and you don't actually have to know exactly if you're on the right track or not. Okay, so why don't we go to the next problem? I think here's a good here's a good problem to show motivation of some invariants. So let's say we have some convex 2n gon, 2n gon. Okay, so S is set of triangles where with vertices, let's say this polygon is called P. So S is set of triangles. Let me draw this better. Triangles with vertices are vertices of P. So S, the size of S would be 2n, choose 3, right? You're choosing any possible 3 points from S. and you're making that into a triangle. And what we want to show is that, I guess I should number my problems, but I forgot which. I think this is problem 3. So why don't I just do this problem 3, just so it's easier for people to read if they're looking at the slides later. Want to show any point. I guess what should the I guess I already used P, so I'll just name the point X. Any point X is in an even number of triangles in S. So why don't we go through some simple examples where so let's do some experimenting. The simplest example would be just a square, right? Where could the point be? Well, you can have something like outside, right? So here you would have 0 triangles. It's inside 0 triangles. Here it would be inside 2 triangles, right? And it's the same everywhere else. I'll just draw them in. So we're inside 2 triangles, right? Why don't we go to a hexagon? I guess the square example is not actually too helpful because, I mean, it's just too obvious. So why don't we go through this? I don't actually want to draw in. Anyways, so the point outside is always 0, right? The point outside is always 0. Let's draw a point here. So what triangles would this be in? So we can have this triangle. So that would be 1. I'm just going to use a different color. This triangle is another one. This triangle is another one. And this triangle is another one. Do we have any more? I think that should be it, right? Yeah, I think that's it. So we have exactly 4, right? Why don't we go through one last example? I'll draw another hexagon since we already kind of took up a lot of space. So what about something like, I'll draw on the diagonals this time so it's easier to see things. Wait, that's not good either. Okay, what about let's have our point. I should draw it in red. Why don't we have it here? How many triangles would this be in? Well, we have this triangle. We have this triangle, so that's 2. We have our third triangle here. I think we want to prove that it's even, so I think I'm missing 1 triangle. Oh yeah, this, or maybe even 3 triangles. I think I have them all. This triangle right here. I think this is all of them. I could be very wrong. Yeah, there are more triangles. Let me attempt to draw all of them. So there's this triangle, so that brings us to 5. Let's see. Oh boy. Wait, we have 1, 2, 3, 4, 5. Wait, do we have 6? 1, 2, 3, 4, 5. No, we have 5 right now. I think I'm definitely missing 1 triangle, aren't I? Huh, that's really weird. I'm pretty sure that's all the triangles, right? Okay, I see which triangle I'm missing. I'm missing the big triangle right here. So that brings us to 6. So this would be 4. Okay, so what one thing I guess that I can just say that some of you may have noticed is that if you draw in all the diagonals, right, of this polygon, you have a lot of regions, right? So we have 12 diagonals total and 6 sides, and that means that we have a lot of regions. So diagonals split into regions. And the point only depends on the region, right? it doesn't matter if 2 points are in the same region, then they're basically the same, right? Because the triangles only care about the region, so only regions matter. And we want to prove something for all regions, right? In this case, in this problem, we're given the invariant, which is nice. We're given that we're given the invariant that everything has to be even. In a different problem, maybe the problem would be asking something else, and we would have to somehow conjecture that all the points are in an even number of triangles, and then we would have to make an invariant that way. That would be much harder, right? Because it's one thing to prove something, it's much harder to actually come up with something before knowing it's true, right? Because even if you notice it, it's kind of a risk that you have to take to think like, I'm noticing that this happens a lot of the time, so I think this may be true, but it's like kind of hard to commit to trying to prove it, right? And sometimes that is another difficult part of Olympiads, just like deciding what type of strategies you should use on a problem. So I guess here, so in this case, we're looking at the most basic, I guess, strategy 1. Most basic is regions, right? Regions are the most basic thing in this problem. In particular, we want to prove for all regions, right? So why don't we look at regions that are next to each other? Because if we want to prove that they're both even, then the difference of the number of triangles should be even, right? Adjacent, or I should say adjacent. Let's say we have like some region here, and we have, I should draw this better. Let's say we have some region here and some region here, right? I'll call this A and B. And why don't I just, and these regions are touching somewhere, right? So like this is a diagonal, so this would be like X and Y. And if we want to somehow use these regions, basically, what if we like move the point? So we want to somehow use the difference, right? So if we move the point, move point A to B, what changes? Well, the only thing that changes is different color. Only triangles with side xy, right? So only the triangles with side xy change. Nothing else changes, right? Because we're only crossing the line xy. And now let's draw in some other points. So we have some k points here. Let's say we have like let me draw I'll just draw it here. So we have like I'm not actually sure how to like clearly draw this polygon. So like let's say the green thing is the polygon P. I know I'm drawing it as a circle, but just like pretend that there's vertices. So let's say that this thing has k vertices in P on this side. Then this side would have 2n minus 2 minus k vertices, right? So if you move from A to B, if move if move A to B, we lose k triangles, and we gain 2n minus 2 minus k triangles, right? So in total, we get 2n minus 2 minus 2k triangles. And we see that this is even, right? So even. And that means that, what does this mean? This means that, okay, so conclusion, adjacent regions have same parity. By parity I mean like the parity of the number of triangles it's in. And of course the outside region has 0. Outside is 0. and if you notice, like, you can easily prove that all the regions are like somewhat, you can like travel from one region to another, so all regions connected, and we're done. Right, because this means that if any two adjacent regions are the same parity, they're both even, then, and any adjacent regions are even, then we also have that every region is even because one region is even from one, just the outside is 0, which is even. Okay, let's see. Why don't we try, I'll just quickly go over this problem because I think it's pretty useful. It's it just goes over some coloring arguments. So P4 really quick. Can we tile 8 by 8 with missing corner with 1 by 3s with 1 by 3s? The idea is, well, first of all, I won't draw in the 8 by 8 with the missing corner. It looks something like this. So like this would be 7, 8, 8, 7, 1, 1. So first of all, this has 63 squares. So 63 is obviously divisible by 3. So, well, first of all, the answer is no. So I'll just give you guys that. And you can try to, well, I guess if you were to see this problem in the wild, like you would just try to tile it, and then you would not be able to tile it, and then you would just like try to see whether we can. Or I guess that's another topic I can go over, but I won't go over it today. So like whether the answer to the problem is yes or no. You kind of have to balance it. You can kind of think whether a problem is yes or no, but unless you have a very strong intuition on why, sometimes the best strategy is try to prove both, right? And then hopefully you can prove one. And then proving one would mean you can just not prove the other, right? Because it can either be yes or no. So in here, the answer is no. So how do we prove this? Well, what kind of shapes can we tile by 1 by 3? First of all, what can we tile? Let's go to the dominoes aside. Let's look at dominoes. Dominoes, so like dominoes have, if you color, in the dominoes case, you might have seen this already from other Olympiad resources. So you can just color checkerboard, right? That's pretty easy. Since dominoes have one white, one black. Right, it's always like this. If you color the board black and white, then you always have one black and one white, right? So can we do the same thing with the 3 domino, the tramino, with 3 different colors? Like let's say white, blue, and black. Because yeah, can we somehow color this? Can we color board? With 3 colors in the same way? The answer is yes. I'll draw a line here. Let me create a new Jamboard. Okay, so how do we do this? Well, you just, okay, so like let me draw my board. I'll just draw part of the board. So you start by you start having just like one corner as your white square, and then all the ones to the right, or you kind of like tile the diagonals, right? So here you would have like something like this, and then you would have another diagonal of whites, and then you would have a final diagonal of blues. So wait, am I doing this correct? Yeah, I am. Right. So so this would be your coloring, and what you notice is that any 3 by 1 always has. It doesn't matter what your board looks like. Any 3 by 1 in the board must have exactly 1 black, 1 white, 1 blue. I'll just finish coloring just because. And if color are bored, number of each color is not the same. And you can just like color it yourself. I won't go over it right now, but it's not the same. So like this does not work. So the answer would be no. Okay, why don't we go to the next problem? Okay, so now I guess we can move on to monovariants. So now I guess this is P5, monovariants. After this, I think, or after a few more problems, I think we can solve some harder problems. Like this is just some introduction. I guess some of these problems are hard. It depends on what skill level you are. Okay, so we have a graph. If you're not familiar with graph, just like put in the chat or something. This is a combinatorial graph. All vertices have degree at most 3. Yeah. As most 3. So prove can split vertices should be nice. 2 sets such that every vertex at most or I guess at most one neighbor. So like if you only take in the same set. So why don't I don't know if that's very clear for those of you who are not so familiar with graph theory. So if you have something like I don't know, like a square, everything, or like a fully connected square, so everything has degree 3, right? So if we kind of split this into A, this is A and this is B, then every vertex has at most one neighbor in the same set, right? So if we just drew A here and we just drew B, everything has degree 1 in the induced subgraph. That's what it's called. If you take the vertices and you only consider edges that are between vertices in the vertices that we just chose. So how do we do this? We want to somehow choose some kind of monovariant. Well, this is not a process, right? First of all, this is not a process problem. There's no process here. It's just asking us that we can do this. So it's not a process. Just prove is possible. And it's really hard to do I'll just say it's really hard to do a construction here, right? A lot of times when it's like a problem is asking you to prove that it's possible, you just like find a construction, right? But here it's like over all graphs with degree at most 3, so it's like doing a construction is not possible. So the thing is, so the idea is, well, I'll just tell you this idea because it comes up a lot. So like next time when you see it, you'll kind of like hopefully remember it. So the idea is start from split, from a splitting and keep on improving it until you can't. And then at the end you should be done. At end should be good. This does not always work like this strategy. It's just a strategy that you might want to consider. Like if you just consider starting with any type of just like some random splitting, and then you want to make the splitting better, right? Somehow better. Um, so, so how do we make this better? Ah, well, if you have something like, so if you have something like x here, and it has an a, um, let me use a different color. So this is set A, and this is set B. If you have X things here, right, and let's just say it has two neighbors, A and B, not A and B, P and Q, because I already use A and B, and then you're connected to a guy Y here, then if you moved X over, if you moved X over, right, it would be better, right, because then if move X, if you just move X, then is it better? Uh, well, well, first of all, if you move X, oh wait, I noticed that my screen is not displaying. Okay, there we go. If you move X, then well, first of all, X is not good because we want to prove that everything has at most one neighbor in its own set. So if X has neighbors P and Q, that's not good. If we move it to set B, then since X has at most two neighbors, then now it has at most one neighbor, right? The neighbor is Y. It could have zero neighbors. Maybe Y does not exist. I'm just like writing the worst case. But the thing is, if we're only looking at the number of vertices that are bad, then if Y has another vertex Z, I'll just draw this inside of B, then then the Y would become bad, right? But the thing is, you notice is that number of edges decreases within. This is within each set A and B. So like we're only considering edges between. It's not showing up for some reason. Uh, Well, anyways, I just like wrote that the number of edges should always decrease because if you look at each, I guess I can't show you anymore. Wait, hold on. My screen seems to be frozen. Yeah, I'm not sure what's going on. Maybe I should stop sharing and then share again. Okay, let me just restart the share.